In this video, we're going to be going over tension members. And these are for steel members. And for all the steel problems, all the steel design problems, I'll be using the AISC 14th edition, which is the blue manual, the light blue manual. Again, there are slight changes from edition to edition, but for the most part, things should stay the same. So the design of tension members can be found in Chapter D. And in that chapter, we find that there are two design checks that we need to do. First, we need to check yielding on the gross section. And then second, we need to check rupture on the net section. So, for yielding on the gross, if we turn to Chapter D, we see that equation D2-1 tells us that Pn equals Fyag. Now, this Ag is the gross area. So that is the area with no holes. It's just the straight up area of whatever section you're looking at. So if we had a quick example, let's just say we've got this angle here. So it's an L 4 by 4 by a quarter. And let's just say these are 3/4 inch diameter bolts. And that's typical for all three of those. And of course, we've got our tension force pulling on that. And also, let's say this is a 36 steel. So if we wanted to check the yielding on the gross section, we've got our equation Pn equals Fyag. So for A36 steel, we know that Fy equals 36 KSI. Now, if you didn't know that, that is given to you in, let's see here, table 2-4. It gives you all the different types of their ASTM designations and their FYs, so their yield stress. So that's all tabulated for you in table 2-4. Now for a 4x4 by 1/4, AG is going to equal 1.93 inches squared. And that's given to you in table, let's see, 4x4 by 1/4 is given to you in table 1-7. So now we've got both of those. We just plug those into this equation. So 36 KSI times 1.93 inches squared. And we'll get PN equals 69.48 kips. And of course, from chapter D, we can see that phi equals 0.9 for yielding on the gross. So phi PN is just going to be phi times PN, which is going to be 0.9 times 69.48 kips, which is going to be equal to 62.5 kips. So that there is the tensile capacity for yielding on the gross section. Now, the second one we've got to check for a tension member is rupture on the net section. So again, in chapter D, we can use, let's look up that equation really fast. Let's see, it's going to be equation D2-2. And that says PN equals FUAE. So if we use the same section as above, we can find FU equals 58 KSI. And that comes from that same table where we found FY. So that's table 2-4 that gives you that information. Now, next we've got to find AE, which is defined in equation D3-1 as AE equals AN times U, where U is a shear lag factor and is given in table D3.1. And AN is your net area. So that's going to be your area. It's going to be your gross area. Subtract that whole right there. So for our gross area, we took the area across this section right here. So this here is your gross, and this here is going to be your net. And it's the area as if you were looking, if you picked up the angle and looked at it that direction, it's going to be that area that you're looking at. So it's this cross-sectional area or this cross-sectional area there. So to find our net area, if we calculate that first, so let's find AN. So again, it's going to be your gross area minus your projected bolt area plus any staggers that you have in your bolts. So if you add staggers in your bolting, then it actually gives you strength. But in this example, all of our bolts line up. There is no stagger. And so for our example, that's just going to go to 0. However, if we did have staggers, you're going to use an equation for that, which I will give you in a minute when we look at staggers. So we got AG we found above is 1.93 inches squared, and that came from table 1-7. And then our projected bolt area is gonna be just this area across here right there. So we know that the bolts going in those holes are going to be 3/4 inch bolts. But we've got to account for some tolerances when they're drilling those holes. So we add 1/16 inch and another 1/16 inch just for those tolerance purposes. So then we can just plug that into our calculator. And I'm going to get the net area equals 1.055 inches squared. And then we can look up our shear lag factor in table D3.1, and we get that U equals 1.0. So we can calculate AE as being 1.055 inches squared times 1.0 equals 1.055 inches squared. So now we've got our AE, we've got our FU, so now we can just plug those into that equation. So we're gonna get that PN equals 58 KSI times 1.055 inches squared, which is going to be equal to 61.19 kips. Now, if we go back to chapter D, we see that for rupture on the net, phi is going to be equal to 0.75. So our phi PN is going to be 0.75 times our 61.19 kips. And that's going to be equal to 45.9 kips. So that's going to be equal to the tensile strength for rupture on the net section. So our total tensile strength is going to be the controlling of rupture on the net or yielding on the gross. So now you can think about this as if we had this section and we started pulling on it little by little by little. So if we started pulling in increments of 10 kips, which value, which phi PN are we going to reach first? 45.9 kips or 62.5? We're going to reach the 45.9 kips first, so therefore it's going to rupture on the net section at 45.9 kips before it even yields on the gross. So therefore, rupture on net controls, and phi PN is going to equal the 45.9 kips. And that is going to be your tensile strength of that particular section. So if we come back, let's take a look. Let's take a look at if there are staggers. Now this is the example 2 of our written examples. So as you can see here, we've got some staggers in our connection right there. So these bolts don't line up vertically or horizontally. They line up diagonally, so therefore there's a stagger there. So of course for this example we went through, we checked the yielding on the gross. And then when we're checking rupture on the net, we've got to include those stagger planes that was mentioned before. And this is the equation for that. So it's the spacing squared times the thickness of that member divided by 4 times the gauge. So we can see from this image down here, the gauge is the distance perpendicular to your tension force, and the spacing is parallel to your tension force. Now, also, when you've got staggers like this, you're going to have different failure planes. And so you have to go through and identify all the different scenarios in which this member could rupture at those failure planes. So for here, it could just come straight across here, and that's going to be our first failure plane. But it could also come down through here and then tear through that way and down here. So we've got our failure plane 1, 2, 3, which is that vertical one, or this wonky one here, the 4, 5, 2, 3, where it could also fail. So we've got to check our AN for both of those. And then you pick the smaller of those two, and that's the one that's going to control. So as you can see here, we checked AN for both of those situations, and we found that failure plane 2 actually controls. So that's where it would fail if it's going to fail and rupture. So again, remember to add in your staggers if you have them. But as you can see for this first plane, there isn't a stagger in that plane, so that's just 0 right there. And then you just follow it through, and you can find your VPN that way. So that's just a look at two different examples for what can happen in different scenarios for tension members. Now, if you have any questions about tension members, feel free to reach out to us. You can head over to our homework help page or our tutoring page, and we'll be happy to answer additional questions for you there.